Welcome back to Understanding Quantum Information and Computation. My name is John Watrous, and I'm the Technical Director for Education at IBM Quantum. This is the 10th lesson of the series, and it's the second lesson in the third unit, which is on the general formulation of quantum information. This lesson is about channels, which represent changes in systems that store quantum information. This includes useful operations, like ones performed by unitary gates in quantum circuits, as well as changes that we might prefer to avoid, like noise. We can also describe measurements as channels, and that's something that we'll get into in the next lesson. The term channel comes to us from information theory, which, among other things, studies the information carrying capacity of noisy communication channels. So, when we think about channels, we're thinking abstractly about communication channels. It might seem kind of odd to think about a complicated computation as a communication channel, but we need a word to refer to the general notion of a process that changes information in some way, and for better or worse, the word channel has stuck, no doubt due in large part to the enormous impact that information theory, and in particular the work of Claude Shannon in the 1940s, has had on quantum information and computation. Here is an overview of the lesson. We'll start with the basics, including the definition of what a channel is, as well as how unitary operations in the simplified formulation of quantum information can be described as channels. We'll also talk about the fact that convex combinations of channels are channels. And if you're wondering why this notion of convexity keeps coming up, it's because it really is a fundamentally important mathematical notion in the theory of quantum information. We'll also see some examples of channels, specifically qubit channels, which will reappear from time to time throughout the remainder of the lesson. In the second part of the lesson, we'll talk about three different ways that we can represent channels mathematically. And in particular, we'll talk about Stinespring representations, Kraus representations, and Choi representations, which are named after three people whose work was important in the development of these different representations. And in the third and final part of the lesson, we'll discuss a mathematical proof that establishes that these three representations are in fact equivalent, as well as the fact that they all correctly characterize the definition of what a channel is. It's a really cool mathematical proof in my opinion, and hopefully it will add some clarity to these different representations, how they relate, and how they work in general. We'll start with the basics and address the question, what are channels? As I already suggested at the start of the lesson, channels describe changes, specifically discrete time changes, in systems that store quantum information. Here, when we refer to a discrete time change, we're just thinking about a change that occurs between two distinct moments in time, as opposed to a continuous process, for instance, that makes sense to think about over infinitesimally small time periods. Channels include useful operations like unitary operations that are performed by quantum gates and circuits, as well as changes due to noise, for instance. For the purposes of this lesson, though, we're mostly going to be thinking about channels in abstract mathematical terms, and there won't be any particular need to distinguish between what's useful and what's not. Typical names for channels include the uppercase Greek letters phi, psi, and xi, and we'll use different letters to refer to some specific channels. In the simple situation in which we have some system that's in a state described by some density matrix rho, and we apply a channel phi to that system, the result is a system whose state is described by the density matrix phi of rho. So we're thinking about a given channel phi as being a function that can be applied to density matrices of a particular size, or in other words, density matrices of a particular system that we're applying this channel to. There are a couple of requirements that channels must satisfy in order to be considered valid channels. First, channels are linear mappings. This is completely analogous to the situation we have both in the simplified formulation of quantum information, where operations on quantum state vectors are necessarily linear, as well as in the standard formulation of classical information, where probabilistic operations are linear. You could choose to question this basic requirement of linearity if you really wanted to, but if we want a theory that's consistent with both probability theory and the choice to represent quantum states with density matrices, then we don't really have any choice and we just have to accept that channels are linear. The second requirement is that channels transform density matrices into density matrices. That makes perfect sense because if we've chosen to represent states of systems with density matrices and we apply a channel to a system that's in some state, then the result has to be a valid state and therefore represented by a density matrix. There's a very important point to add here though, and that is that this requirement has to be true not only if we apply a channel to an isolated system whose state is described by a density matrix, but also if we have a compound system whose state is described by some density matrix, and we apply the channel to just part of that system. So those are the requirements that we place on channels. And we can see that they are very much analogous to the requirements that we have for operations in both the simplified formulation of quantum information and the standard formulation of classical information. In the simplified formulation of quantum information, operations are represented by unitary matrices because they correspond precisely to the linear maps that always transform quantum state vectors into quantum state vectors for a given system. And similarly, probabilistic operations are represented by stochastic matrices because those are the ones that always transform probability vectors into probability vectors. Here we're working with density matrices, and there is this added requirement concerning compound systems that turns out not to be necessary for quantum state vectors or probability vectors, but otherwise the requirements are analogous, and in some sense are forced upon us by the choice to represent quantum states by density matrices. Here are some further details about channels, including a convention for how we'll think about the input and output systems of a channel throughout the lesson, as well as some more detail about the requirement that channels always transform density matrices into density matrices. First, every channel is assumed to have an input system and an output system. We can name these systems however we choose, but throughout this lesson, I'm going to use the name X to refer to the input system and the name Y to refer to the output system. Conceptually speaking, the channel transforms the input system into the output system. So the input and output systems never simultaneously coexist. We start with X, the channel is applied or performed, and the result is that X has been transformed into Y, whose state is determined by the linear mapping associated with the channel. The input and output systems for a channel don't need to be the same, and in particular, they don't need to have the same number of classical states. However, it can be that the input and the output systems are actually the same system, or in other words, X equals Y, in which case we're simply imagining that phi is changing the state of the system. And indeed, this is very often the situation that we're interested in. But this possibility is consistent with the first bullet point, in the sense that we never have the input and output systems existing as two separate systems at the same time. And in any case, it's going to be convenient for the purposes of this lesson to use different letters, namely X and Y, to refer to the input and output systems, just to help us to keep things straight. Now let's go into a little bit more detail about the requirement that channels always transform density matrices into density matrices. Let's suppose that we introduce a new system, Z, into the picture. And let's give the name gamma to the classical state set of this new system. Imagine now that we form a new compound system, Zx, consisting of the new system together with the input system X of a channel phi, and suppose that this compound system is in a state described by a density matrix rho. This can be an arbitrary quantum state of this pair, but whatever state it is, it's always possible to express the density matrix rho in the form that's shown on the screen, where both A and B range over the classical state set gamma, and each rho AB is some matrix whose rows and columns correspond to whatever the classical state set of X is, and we don't need to give that classical state set a name at this point. Just to be clear, each rho AB is not necessarily a density matrix on its own, but the entire matrix rho is necessarily a density matrix. When we apply the channel phi to the system X, it gets transformed into Y, and so we're left with the pair ZY. And the way that we determine the state of this pair after performing phi on just X is to evaluate the linear mapping phi on each of the matrices rho AB. Another way to say this is that we take the tensor product of the mapping phi with the identity mapping on square matrices having rows and columns corresponding to gamma, and that in turn corresponds to doing nothing to this new system Z. But this is an equivalent description, and it doesn't necessitate going into any details about tensor products of mappings of this form. They do, however, work in a pretty straightforward way that's analogous to how they work for vectors and matrices. One way to think about this visually is in terms of block matrices. And if we make the simplifying assumption that the classical state set gamma consists of the integers between 0 and m-1 for some positive integer m, then it becomes easy to write all of this down as is shown right here. And now, to reiterate the requirement that we're placing on phi, in order for it to be a valid channel, we must always obtain a density matrix from this process. And this has to be true regardless of what choice we make for the system Z, as well as the choice we make for rho, provided that it's a density matrix. That might seem like a pretty strict requirement, and it might also seem like it's very difficult to check. But as we'll see by the end of the lesson, it's actually not so strict or difficult to check. And in particular, we have nice mathematical characterizations for this condition, which are connected with the different representations that we'll talk about a bit later in the lesson. Now let's take a look at some examples of channels, starting with an entire category of channels called unitary channels. In simple terms, these are unitary operations just like we have in the simplified formulation of quantum information viewed as channels. To be precise, suppose that U is a unitary matrix that represents a unitary operation on a system X. So, in the simplified formulation of quantum information, we would multiply this matrix to a given quantum state vector to determine the action that that operation has on that quantum state. The way that this works for density matrices is that we multiply the density matrix on the left by U and on the right by U dagger. In mathematical terms, we refer to this operation as conjugation by the matrix U. This is consistent with ket psi bra psi being the density matrix that describes the state represented by the quantum state vector psi, and it's pretty easy to check that. In particular, if we were to perform U on the quantum state vector ket psi, then we'd get U times ket psi, and its density matrix representation is given by that vector times its conjugate transpose, which is U times ket psi times bra psi times U dagger when we evaluate the conjugate transpose of U times ket psi. So, the way that this channel is defined makes sense for pure states, and when we combine this with linearity, we see that it makes sense for density matrices in general, owing to the fact that every density matrix can be expressed as a convex combination of pure states. This definition always gives us a valid channel for any choice of a unitary operation U. In particular, conjugating by a unitary matrix like this doesn't change the trace of a matrix, and if we conjugate any positive semi-definite matrix by any matrix at all, we'll get another positive semi-definite matrix. And it's pretty easy to get that directly from the definition of positive semi-definite matrices. So density matrices always get mapped to density matrices, and all of this remains true even if we tensor U with the identity matrix of any size, which is equivalent to applying this channel to just part of a compound system. Here's a really simple example of a unitary channel. Suppose we take U itself to be the identity matrix. This is very obviously a valid channel called the identity channel. Doing nothing at all is certainly a linear operation, and if we start with a density matrix and we do nothing to it, it's still going to be a density matrix. So this is a valid channel. People use different symbols to denote this channel. Sometimes it's exactly the same symbol we use for the identity matrix, which can be a little bit confusing, but it generally isn't. Here I'm using the letters ID, short for identity, just to avoid any confusion, and this notation is also pretty common. It might seem like a very boring channel, but in the context of information transmission, it's actually a perfect channel, where the receiver gets exactly what the sender sends, which is typically what one wants most in that context. Another way we can obtain lots of examples of channels is to take convex combinations of channels, or in other words, to average them together. And the fact that we can do this is an important aspect of channels. To explain this in more detail, let's start with two channels, phi 0 and phi 1, let's say, along with a real number p between 0 and 1. And just to be clear, we're assuming that these two channels have the same input system, which is x, as well as the same output system, which is y. And now consider what happens if we decide to apply the first channel, phi 0, with probability p, and otherwise, with the remaining probability 1 minus p, we apply the second channel, phi 1. For instance, maybe we randomly choose a bit with those probabilities, and then use this random bit to determine which channel to apply. By doing this, we're effectively applying a new channel, which we might call psi, that's given by a convex combination of the two channels that we started with, and which we can express as is written on the screen. We can always take linear combinations of linear maps like this, by the way. And the way that a linear combination of linear maps is defined on a given input is that we just take the same linear combination of the outputs. That might look sort of trivial, but it makes sense. The output we get from this hypothetical scenario is simply the weighted average of the outputs we would get from the two original channels. Nevertheless, this is a new channel, and if phi 0 and phi 1 were indeed valid channels, then for sure this new mapping will also be a valid channel. Another way to say that, in mathematical terms, is that the set of all channels from a given input system to a given output system is convex. And that's an important mathematical property of channels. We can do this more generally. If we have m channels, phi 0 through phi m minus 1, say, along with the probability vector that tells us what the probability is for each channel, then we get a new channel by averaging the channels accordingly. So in some sense, this is an endless source of new channels. For example, the class of so-called mixed unitary channels is what we get by taking convex combinations of unitary channels. That is, if we have m unitary matrices u0 through um-1, all having the same size, along with the probability vector, then if we take the weighted average of the channels corresponding to the individual unitary matrices, as is shown here on the screen, then we'll get a channel. And channels that can be written like this are called mixed unitary channels. Not every channel is a mixed unitary channel. We can't get every channel this way, but they do come up quite a lot. Next, we'll look at a few specific examples of channels. These will all be examples of channels from 1 qubit to 1 qubit, which are called qubit channels for short. The first one is called the qubit reset channel, and the idea is that this channel resets a qubit to the 0 state. Here we're using the capital Greek letter lambda to denote this channel, and the way that you can remember what this channel does is to think about the Bloch sphere. Capital lambda kind of looks like an arrow pointing up, and the 0 state is at the top of the Bloch sphere, so it's as if it's pointing to the location of the output. The way it's defined in mathematical terms is that lambda of rho equals the trace of rho times ket 0 bra 0. So if we evaluate it on any density matrix rho, we'll get the 0 state as a density matrix. It's natural to wonder why we need the trace. Couldn't we simply define lambda of rho to be ket 0 bra 0 without the trace of rho in front? And the answer to that question is no. Channels need to be linear maps, and it wouldn't be linear if we removed the trace of rho. Also keep in mind that sometimes we need to know how a channel works as a linear mapping on non-density matrix inputs. For example, as we saw earlier, if we want to know what a channel does when we apply it to a compound system, we need to evaluate that channel on the individual blocks of a larger block matrix. And although the entire block matrix may be a density matrix, the individual blocks generally won't be. So let's see exactly what this channel does when we apply it to just one part of a compound system. And more specifically, what it does when we apply it to one of two qubits that form an e-bit. To be precise, suppose A and B are qubits that, as a pair, are in the phi plus Bell state, and we apply lambda to, say, the first qubit A. To figure out what happens, let's first express the phi plus state as a density matrix, and for the sake of this example, let's use Dirac notation to do that. Here's the phi plus state as a quantum state vector, and here's what we get when we multiply this vector to its conjugate transpose and expand it all out. We can then apply the channel to the first qubit and evaluate what we get. Here's lambda applied to the first qubit, and here's what we get when we evaluate each of the terms. The trace of ket 0 bra 0 is 1, and so is the trace of ket 1 bra 1. So in those two cases, the output of the channel is ket 0 bra 0, and that explains the two terms in the answer. The trace of ket 0 bra 1, on the other hand, is 0, as is the trace of ket 1 bra 0. And so those two terms evaluate to 0, and therefore don't contribute anything to the answer. We can now simplify a little bit, and what we obtain is the 0 state for the first qubit, which is A, and the completely mixed state for the second qubit, which is B. Notice in particular that we did not get a plus state for B, which wouldn't necessarily have been a bad guess if we didn't know anything about density matrices and we just looked at the quantum state vector representation of the state, but that's not how this channel works, and there isn't any channel that could possibly work that way. The channel lambda is called the qubit reset channel, but the way it works is really more like throwing the input qubit in the trash and replacing it with a fresh qubit in the 0 state. But this in fact is the only qubit channel that always outputs the 0 state. Here's another example of a qubit channel known as the completely dephasing channel. This one is denoted by delta, and the way that it works is that it leaves the diagonal entries of any 2x2 matrix alone and zeroes out the off-diagonal entries. Delta is the Greek letter equivalent of D in the Latin alphabet, and that's short for diagonal, so that's one way to remember what this channel does. We can alternatively express this channel using Dirac notation as is shown on the screen. And just to be clear, the output is always a 2x2 matrix, so in particular, the two 0 outputs refer to the all 0 2x2 matrix. We often do this, and we've seen this before in this series. The symbol 0 is generally used, perhaps ambiguously, to mean the 0 element of whatever thing we're talking about, whether it's scalars, vectors, matrices, or whatever. Let's do the same thing that we did previously for the qubit reset channel and see what happens if we apply this channel to half of an e-bit. The setup is the same, so I won't go through that part. and the result is the state shown on the screen, which is essentially a shared random bit. So what this channel did was basically to convert an E bit into a perfectly correlated pair of classical random bits. And that's consistent with a more general interpretation of this channel. By zeroing out the off-diagonal entries of a density matrix, we're effectively throwing away the quantum stuff in a density matrix, leaving a diagonal density matrix that represents a classical probabilistic state. Another way to think about this is that this channel represents a perfect noiseless classical channel that transmits a bit. So if we put a 0 state or a 1 state, or a convex combination of those two states into the channel, then that state comes out unchanged. But if you try to put a quantum state into it, like a plus state for instance, it's as if the channel measures that state with a standard basis measurement and then transmits the classical result. One final example of a qubit channel is the completely depolarizing channel. What this channel does is to always output the completely mixed state. So it's similar in some sense to the qubit reset channel, except that we get a rather less useful completely mixed state out rather than an initialized qubit. A natural way to think about this channel is that it represents an extreme form of noise. And as far as qubit channels are concerned, it really doesn't get any noisier than this. I don't have a good mnemonic to share for remembering what this one does, other than to say that omega is the last letter of the Greek alphabet, and it's sometimes associated with the end of all things, and perhaps this is what happens to all qubits eventually. As far as noise goes, it's pretty extreme. But one thing that we can do is to consider a convex combination of this channel and the identity channel, with perhaps a small probability epsilon for complete depolarization. This is a less extreme form of noise, where a given qubit state will mostly be left alone, but there is some small chance that it becomes completely mixed. Geometrically, we can think about this as a slight contraction of the Bloch sphere toward the center. And by the way, we can do something similar with the completely dephasing channel to model the process of decoherence, for instance, where things become slightly more classical through some process. So those are three basic examples of qubit channels, and we'll come back to them mainly as a source of examples throughout the remainder of the lesson. Next, we'll discuss mathematical representations of channels, starting with a basic question. Linear mappings from vectors to vectors can always be represented by matrices in a familiar way, which is that the action of the linear mapping is described by matrix vector multiplication. But channels are linear mappings from matrices to matrices, not vectors to vectors. So, in general, how can we express channels in mathematical terms? Sometimes, for special channels, we'll have a simple formula that describes them, and that was the case in the examples of qubit channels that we already discussed. But that isn't practical in general because there won't always be such a nice formula. As a point of comparison, in the simplified formulation of quantum information, we use unitary matrices to represent operations on quantum state vectors. Every unitary matrix represents a valid operation, and every valid operation can be expressed as a unitary matrix. So in essence, what this question is asking is how do we do this for channels? And the answer to this question is that there are in fact multiple ways to represent channels in mathematical terms. In particular, we'll discuss three different ways of representing channels that are named after three individuals whose work played an important part in their development: Stinespring, Kraus, and Choi. First, we'll see how these different representations work, and then in the last part of the lesson, we'll see how the three representations relate, and in particular, how we can convert between them. We'll also see that these representations precisely capture the requirements that we have on channels, namely that they're linear mappings, and that they always transform density matrices into density matrices, even when they're applied to just one part of a compound system. First up are Stinespring representations. William Forrest Stinespring was a mathematician who didn't work on quantum information, and Stinespring representations, as I'll describe them, are in some sense just a derivative of his work on operator theory in the 1950s, but this work was most certainly an important part of the development of the mathematics that quantum channels are based on. The idea behind this way of representing channels is that every channel can be implemented in a certain way that I'll now describe. First, we form a compound system consisting of the input to whatever channel we're implementing, together with an initialized workspace system. Then, a unitary operation is performed on the compound system, and finally, whatever part of the resulting compound system corresponds to the output of the channel is left alone, or output, and the rest is discarded, or traced out. It's helpful to express this in the form of a diagram, and it's simplest to start with the special case in which the input and the output systems are the same. This diagram, by the way, is just like a quantum circuit diagram, except that the wires represent arbitrary systems and not necessarily single qubits. So we start with the input system X being in some state rho. We introduce an initialized workspace system W, and in this diagram, I'm presuming that 0 is a classical state of W, and we're taking ket 0 to be the initialized state of the system. But we could alternatively fix any pure state of W and view that as the initialized state. We then perform some unitary operation on the pair Wx, and then trace out the workspace system and output X. Here in the diagram, by the way, I'm using the ground symbol from electrical engineering to indicate that W is being discarded. That's not necessarily conventional, and you won't find that symbol in Qiskit. There, you just ignore the qubits that you're not interested in. The point is that I just want to have a symbol that makes it clear that we're discarding the system for the purposes of this discussion. In general, we don't necessarily need the input and the output systems to be the same. So we can have, for instance, an output system Y along with a garbage system G that gets traced out. In order for U to be unitary, it has to be a square matrix. So there's an assumption here that the pair GY together has the same number of classical states as the pair WX. For example, maybe these systems consist of qubits, and the input system X consists of 5 qubits, and W consists of 10 qubits, say. So U is a unitary operation on 15 qubits. It could then be that Y consists of just 4 qubits, which means that G consists of 11 qubits. Or maybe these aren't qubits at all. All that's important is that WX together and GY together have the same number of classical states so that U can be unitary. A description of a channel like this is called a Stinespring representation of the channel. Now, it's pretty straightforward to argue that any mapping phi that can be described in this way is in fact a valid channel. In particular, if we start with a density matrix and then tack on an additional workspace system, then we'll certainly be left with a density matrix. We already observed that applying a unitary operation gives us a valid channel. And if we have a density matrix of a compound system and we trace out one of the systems, then again we'll be left with a density matrix. So when we compose these steps, we'll be guaranteed that it always transforms density matrices into density matrices. And it's also linear. What's not at all clear at this point is that every channel can indeed be implemented in this way, for some choice of the workspace system and the garbage system, as well as the unitary operation U, of course. But that is true, and we'll see why by the end of the lesson. Here's an example of a Stinespring representation for the completely dephasing qubit channel. And to be clear, now the wires are qubits, and this is an ordinary controlled NOT gate. It's very simple. The input qubit is on the top, and we introduced a workspace qubit initialized to the 0 state. We then perform a controlled NOT operation, where the input qubit is the control and the workspace qubit is the target. And then the workspace qubit is traced out. Intuitively speaking, it makes sense that this should implement the completely dephasing channel, because the controlled NOT gate kind of acts like a standard basis measurement on the top qubit by copying its classical state onto the bottom qubit, and then the result gets thrown away. But we can also go through a calculation, and of course it's a good idea to do that because we really shouldn't put too much trust in our intuition. We can start by writing down the density matrix representation of the 2 qubits after the workspace qubit has been introduced. And notice that we're using the Qiskit ordering convention as usual, where the bottom qubit is the left one and the top qubit is on the right. We can express this density matrix explicitly as an actual 4x4 matrix as is shown on the screen. And then we compute the effect that the controlled NOT gate has on this density matrix. So we conjugate by the unitary matrix associated with this gate. Once again, keeping in mind the Qiskit ordering convention, so this is the correct unitary matrix. And the result is shown here. In effect, the controlled NOT gate permuted the entries of our original matrix around a little bit, so now the possibly non-zero entries are in the 4 corners. It remains to compute the partial trace, and we could do that directly from the matrix, but an alternative is to convert to the Dirac notation as is shown on the screen. And then it becomes pretty easy to evaluate what happens when we trace out the qubit on the left within each term. And the result is that just the terms corresponding to the diagonal entries of rho survive, And so we've dephased the qubit as expected. As always, check this for yourself at your own pace if you choose to do that. It's a good example to get some practice working with density matrices and with partial traces. That's not the only way to implement the completely dephasing channel. Here's an alternative Stinespring representation for this channel. I won't go through the calculation in detail in this video, but I will show it briefly in case you'd like to pause the video and have a closer look. The way it works is similar to the first one, but the details are different. This time we start with a Hadamard gate on the workspace qubit, which puts it into a plus state. And if we expand out the tensor product, we get the matrix that's shown on the screen. To apply the control Z gate, we conjugate by the associated unitary matrix. And the result of doing that is to inject some minus signs into the matrix. In particular, the last row and the last column both get multiplied by -1. And this time, it would be pretty messy to convert to Dirac notation, so we'll compute the partial trace directly. When we trace out the first of two qubits, what we end up getting is the sum of the two diagonal 2x2 blocks. And so the final result is again that we've dephased the qubit. That was quick, and if you're not used to these sorts of calculations, then take your time and do it slowly. Speed is not important here. To finish off this example, let me mention that there is a pretty simple idea behind this implementation, which is pretty nicely expressed by the last step of the calculation that we just skimmed through. A more succinct way of saying this is that if we average a given qubit density matrix with that density matrix conjugated by the poly Z matrix, then that's the same thing as dephasing. So the completely dephasing channel happens to be a mixed unitary channel, where we either do nothing, or in other words, we perform the identity operation, or we perform a Z gate, each with probability 1/2. Good to know. So in summary, we have two different Stinespring representations of the completely dephasing channel. And that tells us something important, which is that Stinespring representations are not unique. And in fact, there are infinitely many of them for any given channel. Next, we'll discuss Kraus representations of channels, which give us a convenient formulaic way of expressing channels through matrix multiplication and addition. Kraus representations are named after Karl Kraus, who was a physicist who, among other things, worked out a lot of the basic mathematical details of channels and the general formulation of quantum information more broadly. In general, a Kraus representation is an expression of a channel taking the form shown here on the screen. In particular, we have a collection of matrices, which here are named A0 through AN-1 for some positive integer n, and they specify the action of the channel on any given input row according to the formula. In short, we conjugate row by each of these matrices, which are often referred to as Kraus matrices in this context, and then we sum up the result, and that gives us the output. All of these matrices have to have the same dimensions, and specifically, their columns must correspond to the classical states of the input system, and the rows must correspond to the classical states of the output system. If that's the case, then when we take the product ak times row times ak dagger for any choice of k, we get a square matrix whose rows and columns correspond to the classical states of the output system, and so it makes sense that the expression produces a density matrix of the output system. Now, it is not the case that for an arbitrary choice of these Kraus matrices that we get a valid channel. There is, however, a pretty simple condition on the matrices that guarantees that we will get a valid channel, and that condition is the formula displayed right here. Specifically, if we sum up the product of ak dagger times ak over all the values of k, then we must get the identity matrix. And that will be the identity matrix whose rows and columns correspond to the classical states of the input system. So, that condition must be satisfied in order for the mapping defined by the first equation to be a valid channel. And it turns out that every channel does in fact have a representation that takes this form, as long as we take n to be large enough. Here are a few examples of Kraus representations, starting with the qubit reset channel. We can obtain a Kraus representation for this channel by using two Kraus matrices, ket0 bra 0 and ket0 bra 1. So n is equal to 2 in this example. We can plug these choices into the general formula, and we have just two terms, so it's easy to write out the sum. And if we simplify, and recognize that the expression in parentheses is the trace of row, then we see that we obtain the Qubit reset channel. We can also check that the required condition on these matrices is met, and that's a simple matter of plugging the Kraus matrices into the equation and evaluating, and we get the identity matrix as is required. For another example, let's again take a look at the completely dephasing channel. Taking the matrices cat0 bra 0 and cat1 bra 1 works, and that can be checked by expanding out the sum and seeing pretty directly that we get what we need. And again, the required condition is met. An alternative is to take A0 to be the identity matrix divided by root 2, and A1 to be sigma z divided by root 2. And if we evaluate, we see that again we get the completely dephasing channel based on the observation we made about this channel a little bit earlier in the lesson. And once again, the required condition is pretty straightforward to check. As an exercise to work through, if you would find that to be helpful, consider the completely depolarizing channel, which outputs the completely mixed state for every density matrix input. For this one, 4 Kraus matrices are required. It's not possible to come up with a Kraus representation where n is 3 or less. Here's one choice that works, and here's another. So the exercise is to verify that these choices work, as well as to check that the required condition is satisfied. It's worth pointing out that the second alternative basically says that it's possible to completely depolarize a qubit, or in other words, to completely randomize it, by randomly choosing one of the 4 Pauli matrices, including the identity, and applying the corresponding unitary operation to the qubit. And so, the completely depolarizing channel is another example of a mixed unitary channel. The last of the 3 channel representations that we'll cover is the Choi representation. Mandu Choi is a mathematician who works on matrix theory and other topics, and the Choi representation is named in his honor based on a really elegant paper that he published in 1975 that, in some sense, ties all this stuff together. The Choi representation of a channel phi is a single matrix that's conventionally denoted J of phi. And specifically, if the input system has n classical states and the output system has m classical states, then the Choi representation of phi will be an n times m by n times m square matrix. Before I tell you exactly how the matrix is defined, I'd like to mention a couple of its key properties, which motivate the representation in a way that the actual definition itself might not, at least on the surface. First, unlike both Stinespring representations and Kraus representations, the Choi representation is a so-called faithful representation, which means that every channel has just one of them. And that's pretty important because it says that 2 channels are the same if and only if their Choi representations are the same. So, if you have 2 different descriptions of channels, such as 2 different Stinespring representations, or 2 different Kraus representations, or perhaps one of each, and you want to know if they are in fact the same channel, you can just compute the Choi representation and check whether or not they're equal. The second property is that there are simple to check conditions on the Choi representation that are true if and only if we have a valid channel. That property isn't quite so special. We can say the same thing about the other 2 representations, but it's a good property to have nevertheless. And we'll discuss it further in more detail shortly. One more thing to note about the Choi representation is that although we are representing a channel by a matrix, this matrix does not directly represent the channel as a linear mapping. In fact, it's actually more natural to associate the Choi representation with a density matrix that represents a certain state than it is to think about the Choi representation as describing a linear mapping. It is, however, possible to recover the action of the channel from its Choi representation using a pretty simple formula, but it's not so simple as ordinary matrix multiplication. That's enough of a preamble. Let's get to the actual definition. Suppose that we have a channel phi from a system X to a system Y, and assume that the classical state set of the input system X is sigma. We're not going to need to refer to the classical state set of the output system, so for the definition, there's no need to name that one. The Choi representation of phi is then defined by the expression shown here on the screen. We have a sum that ranges over all classical states A and B for the input system, and we're summing ket A bra B tensored with the channel phi applied to ket A bra B. So this representation is defined by a formula. And there are a couple of different ways that we can think about this formula. Before I discuss them, however, let me mention that sometimes the Choi representation is defined in a slightly different way where the ordering of the 2 tensor factors is reversed, meaning that phi of ket A bra B appears as the first tensor factor rather than the second. But the 2 different ways of doing it are equivalent up to this simple symmetry. But what that means is that when you're using this representation, it's a good idea to clarify which ordering you're using. This ordering is the way it's done in Qiskit, And it's also better for describing the representation visually in terms of block matrices, so this is the one that we're going to go with. To be more precise about the block matrix description, if we assume that the classical state set sigma consists of the integers from 0 up to n-1 for some positive integer n, then we can alternatively write J of phi as a block matrix, as is shown right here on the screen. In other words, the Choi representation of phi is the matrix we get by evaluating phi on each of the input matrices that have exactly one entry equal to 1 with all of their entries 0, and then arranging them into a matrix in a pretty natural way. It may not be clear a priori why we would want to form a matrix like this, but it does turn out to be very useful. One thing to notice is that the set containing the matrices ket A bra B, as A and B both range over all integers from 0 to n-1, forms a basis for the space of all n by n matrices. So, if you have this matrix, then you can certainly determine what phi does to an arbitrary n by n matrix by linearity, specifically by taking appropriate linear combinations of the blocks. So the matrix J of phi does in fact uniquely determine phi as a linear mapping. Another way to think about the Choi representation of a channel is that it represents a state as a density matrix when it's normalized, specifically by dividing it by the number of classical states of the input system, which I'll continue to denote by lowercase n. This will always give us a density matrix, which is often referred to as the Choi state of the channel. Here's how this works in more detail. Imagine first that we have two identical copies of the input system, and we consider the quantum state vector psi displayed on the screen, which represents a so-called maximally entangled state of this pair of identical systems. For instance, if sigma is the binary alphabet, then this is a phi plus state, but we can think about an analogously defined state for any choice of sigma, and what we get is a state that's highly entangled. And in fact, it's as entangled as you can get given this choice of systems. To obtain the density matrix representation of the state, we multiply the state vector to its conjugate transpose as usual, and this is what it looks like. And finally, if we think about the Choi representation of the channel divided by n, then we see that it's the state that we would obtain if we were to apply the channel phi to the second system. In the form of a figure, here's what this looks like. We have two copies of the system X in this maximally entangled state psi. The channel phi is applied to the second system, which is the one on the top in the diagram, and the resulting state is the Choi state of phi. Of course, we wouldn't normally give the same name to two different systems like this. It's generally not helpful to give the same name to two different things, but it does make sense in this case just to make this connection with Choi representations. There are a couple of implications that we can immediately draw from this way of looking at Choi representations. One is that because the Choi state is a density matrix, assuming that phi is a valid channel, we conclude that the Choi representation of phi must be positive semi-definite. Remember that it's a requirement that we place on channels that they always transform density matrices into density matrices, and this is just one special case of this. The second implication is that if we take the Choi state for any channel phi and then discard the output system y, then we must be left with the completely mixed state on the input system x. That's because applying a channel to a system and then throwing the resulting system into the garbage is equivalent to just throwing the original system into the garbage. And if we were to do that with our maximally entangled state, the density matrix we'd be left with would be the identity matrix divided by n, or in other words, the completely mixed state for the system X. The idea in more mathematical terms is that composing any channel with the trace on the output system must be equal to the trace on the input system, and that's because channels must preserve trace, by virtue of the fact that they're linear mappings that always transform density matrices into density matrices. Once we have this equation, we can clear the denominator n from both sides to get a slightly cleaner condition. In words, performing the partial trace on the output system of the Choi representation of a channel must give us the identity matrix on the input system. So, in summary, Choi representations of channels are always positive semi-definite, and if we trace out the output system, we're necessarily left with the identity matrix on the input system. As it turns out, these are not only necessary conditions, but they're also sufficient, meaning that if phi is some arbitrary linear mapping, and these two conditions both happen to be true, then it must in fact be that phi is a valid channel. And we'll see why that is the case by the end of the lesson. Let's take a look at a few examples, starting with the completely dephasing channel. To compute the Choi representation, it's just a matter of evaluating the formula. The completely dephasing channel leaves ket A bra B alone when A equals B, and otherwise the output is 0, so the terms in the sum that survive are the ones where A equals B, and the result is expressed on the screen using Dirac notation. We can also view it as a block matrix. Delta leaves diagonal entries alone and zeroes out off-diagonal entries, and so we're left with a matrix having 1s in the upper left and lower right-hand corners, with all of their entries being 0, and that's consistent with the first expression. For another example, let's consider the completely depolarizing channel. Again, we can start by writing down the formula, and just like in the previous example, we don't get any contribution to the sum when A is not equal to B, and this time, when A equals B, we get the completely mixed state. And we can simplify that to obtain 1/2 times the 2x2 identity matrix tensored to itself, which is 1/2 times the 4x4 identity matrix. We can also think about it in terms of block matrices, and naturally we get the same result. And as a last example, let's consider the identity channel for a single qubit. It's an easy one. Here's the formula, and of course the identity channel doesn't do anything at all, and we can think of the result as being twice the density matrix associated with a phi plus state, and that's consistent with what we expect by thinking about the Choi state of this channel. And here it is as a block matrix. Notice in particular that the Choi representation of the identity channel is not the identity matrix, it's this matrix. We've now seen 3 different ways to represent channels in mathematical terms, namely Stinespring representations, Kraus representations, and Choi representations. And we also have the definition of a channel, which is that a channel is a linear mapping that always transforms density matrices into density matrices, even when the channel is applied to just part of a compound system. A very natural and very important question to ask at this point is, how do we know these things are all equivalent? For instance, how do we know that every mapping described by any one of these representations is in fact a valid channel? And how do we know that we're not leaving any channels out? The remainder of the lesson describes how all of this can be reasoned mathematically. If you're willing to accept the equivalence of these things, and you're not interested in how it can be reasoned, then you should feel free to skip the rest of the video. But I personally think the argument is pretty slick. And it's a good example of a particular style of mathematical proof that comes up from time to time in the theory of quantum information. I won't go through all of the details, some of them I'll leave for you, or you can find them in the written content for this lesson where everything is written out in detail. But I do hope to present a reasonably clear picture of how it all works. What we want to do is to prove the equivalence of a collection of statements. And the way that we can do this is to set up a cycle of implications. In particular, we'll start with the definition of a channel, meaning a linear mapping that always transforms density matrices into density matrices. From this definition, we can reason that the Choi representation of this channel must satisfy the 2 conditions we've already discussed. And in fact, we've already done this. This was discussed in the context of the Choi state of a channel. We then forget all about the definition and we work from the Choi representation. And given our 2 conditions on Choi representations, we conclude that there must exist a Kraus representation of the mapping phi. We then do an analogous thing. We forget about Choi representations and we work from an arbitrary Kraus representation, and from it we can reason that there must be a Stinespring representation for the mapping phi. And by the way, these arguments will be mechanical in some sense, which allows us to actually perform the conversions according to the arrows for specific channels if we want to do that. The last implication is to reason that if we have a Stinespring representation for a mapping phi, then that mapping must in fact be a valid channel. And again, we already did that, this time in the context of Stinespring representations. Altogether, these 4 implications reveal that these 4 things are all equivalent, because you can start from any one of them and follow the implications transitively to get to any of the other ones. We'll start with the first implication, which is that if we have a channel phi, meaning a linear map that always transforms density matrices into density matrices, then it has a Choi representation that satisfies the 2 conditions that we identified earlier, namely that it's positive semi-definite, and if we trace out the output system, we get the identity on the input system. And as I mentioned a moment ago, we've already covered this implication in the context of Choi states. In particular, when we divide the Choi representation of a channel by n, the number of classical states of the input system, then we get a density matrix. And moreover, the reduced state of the input system x for that state is the completely mixed state, or in other words, the identity matrix divided by n. Clearing the denominator gives us our 2 conditions, so this implication is pretty quick and easy because we already covered it. Now let's take a look at the second implication. This time we start with the Choi representation of a mapping, which we assume satisfies the two requirements, and our goal is to come up with a Kraus representation for this mapping that satisfies the requirement that we talked about earlier. This implication is quite mechanical in a sense. We'll need a little bit of linear algebra, and it'll mainly come down to manipulating matrices and vectors in a pretty clever way. It starts with the assumption that the Choi representation is positive semi-definite, which is the first of the two requirements that we're assuming are in place. The notion of a positive semi-definite matrix is fundamentally important in quantum information, and not just in the context of density matrices. It's absolutely critical here. We wouldn't be able to make this work without it. In particular, the assumption that JFI is positive semi-definite allows us to express it in the form shown on the screen for some choice of vectors psi 0 through psi n-1 and some choice of a positive integer n. And let me note explicitly that these are not necessarily unit vectors. One way that we can get our hands on an expression like this is from the spectral theorem for positive semi-definite matrices, which was discussed in the previous lesson. Here, we don't see any eigenvalues appearing explicitly like we had in a spectral decomposition, but remember that the eigenvalues of positive semi-definite matrices are always non-negative real numbers, and also keep in mind that we're not requiring these vectors, psi 0 through psi n-1, to be unit vectors. So what we can do is to take the square roots of the eigenvalues and multiply them into the unit eigenvectors we get from a spectral decomposition to get these vectors psi 0 through psi n-1. It's actually not important for this proof that these vectors are orthogonal. We do get that from a spectral decomposition, but we're not going to use that here. And if we had some different expression of JFI like this that didn't come from the spectral theorem, then that would be just fine. We now decompose each of these vectors as is shown on the screen. And this is just like we would do if these vectors were quantum state vectors of a pair of systems x, y, and we were performing a standard basis measurement on the x system. To be clear, we're not measuring anything here. We're just writing these vectors in this form, which is always possible. And now, here comes the trick. We define Kraus matrices A0 through AN-1 by plucking the ket A's off of the front of these vectors, psi 0 through psi n-1, flipping them around so they become bra A's rather than ket A's, and sticking them on to the right-hand side, as is shown in the equation on the screen. One way to think about this is that we're basically folding up these vectors to form matrices, so that if we stacked the columns of AK on top of one another, we'd get back psi k. So these matrices have exactly the same entries as the corresponding vectors, but we've just rearranged the entries differently so that we get matrices. But we can also think about these matrices purely symbolically in terms of Dirac notation, as is written here. And now, at this point, there's an obvious question. Why should this work? Well, let's not dwell too much on why it works. Let's just verify that it does. To do this, let's define a new mapping, which is the mapping defined by these matrices where we're treating them as Kraus matrices. What we can now do is to compute the Choi representation of this new mapping, and we'll see that it's equal to the Choi representation of the mapping phi that we started with. And because Choi representations are faithful, this means that the two mappings are in fact equal. I won't go through the algebra in this video. You can verify that yourself. It's quite mechanical and it's good practice. And everything you need for that is right here on the screen. We haven't said anything yet about the two second conditions in the two boxes, but they turn out to be equivalent. And one way to establish that is to verify the equation displayed here on the bottom of the screen. The letter T here, by the way, refers to matrix transposition, which you can alternatively think about as the linear mapping that turns ket A bra B into ket B bra A. And it's just something that's needed to make the formula work. So, in summary, there's definitely some algebra needed for this implication, but like I said, it's all pretty mechanical. Basically, index gymnastics, as some people refer to this sort of thing. But if you work through it and you give your brain a chance to digest it, you may find that you come away with a better understanding of how Choi representations and Kraus representations relate. The third implication allows us to go from a Kraus representation of a mapping phi, where the usual condition is in place, to a Stinespring representation. This one is pretty similar in spirit to the previous implication in the sense that it's mechanical, and it can be viewed and verified in purely algebraic terms. The idea is actually pretty simple. What we can do is to take our Kraus matrices and form part of a larger matrix by stacking them on top of one another, like is shown on the screen. Once it's filled out, This will give us the unitary matrix U for a Stinespring representation. Unitary matrices have to be square matrices, so we'll have to fill out as many remaining columns as we need to do that, but it won't actually make any difference what they are, as long as we get a unitary matrix. If we momentarily put aside the concern that U is unitary and just focus on the linear mapping that's defined by the Stinespring representation we get from this matrix U, then what we find is that the mapping is equal to the original mapping phi defined by the Kraus representation that we started with. That's another part of the proof that I won't go through in this video. You can find the details in the written content for this lesson, but you may alternatively wish to take some time and work through it for yourself. Just keep in mind, as usual for this series, that we're using Qiskit's ordering convention to interpret the diagram. So W and G will correspond to the tensor factors on the left-hand side in the equations. And by the way, if you do go through it, you'll find that because we have ket 0 bra 0 as the tensor factor on the left-hand side in the equation that we need to verify, the only portion of U that has any relevance is the part given by the Kraus matrices. So as long as we fill out the columns of U in a way that makes it unitary, then we're good. But of course, this requires that the columns formed by A0 through AN-1, when we stack them on top of one another, are orthonormal. And this is where the condition that we place on Kraus representations comes into play. And indeed, it's precisely equivalent to the columns being orthonormal. The relevant mathematical relationships needed to draw this conclusion are shown down here on the bottom of the screen, so go ahead and pause and verify if you choose, or again, consult the written content for further details. In short, what's going on here, in both this implication and in the previous one, is that we're describing the same mathematical operations in different but equivalent ways. The beating heart for all of it, essentially, is matrix multiplication. The fourth and final implication establishes that if we have a Stinespring representation for some mapping, then that mapping must in fact be a valid channel. And as I indicated earlier, we already covered this implication when we discussed Stinespring representations. In summary, and in slightly different terms, introducing an initialized workspace system is a valid channel. That's because tensoring a fixed density matrix to a given density matrix always gives us a density matrix, and it's a linear mapping by the bilinearity of tensor products. Unitary operations are always valid channels, as I discussed earlier in the lesson. Tracing out a system is a valid channel because the partial trace is a linear mapping that always transforms density matrices into density matrices. And finally, compositions of channels are always channels, which is quite simple, but definitely worth observing in its own right. And with the four implications we just covered, we've established the equivalence of our three channel representations along with the original definition of a channel. In particular, we started with the definition of a channel. We saw how that definition implies that its Choi representation necessarily satisfies two basic conditions. Then we saw how those conditions allow us to find a Kraus representation, which in turn allows us to find a Stinespring representation. And finally, we saw that the existence of a Stinespring representation reveals that we do in fact have a valid channel. Of course, there are technical details in there, and it's not necessarily simple, especially when you're seeing it for the first time. But what's interesting and noteworthy here is that these implications are set up in a way that does in fact make things as easy as possible. And in mathematics, you should never feel any shame in taking the easy way out. For example, it's not at all obvious that every channel has a Stinespring representation or a Kraus representation, but it is relatively easy to conclude that the Choi representation of every channel satisfies the two conditions that we've associated with it, and that allows us to follow a more or less algebraic path to the other two representations. In a similar vein, the last implication from a Stinespring representation back to the definition is also relatively straightforward, and it allows us to conclude that we only get channels and no other mappings from Choi representations, assuming that the required conditions are met. And as I alluded to before, the way that we argue these implications are sufficiently mechanical to allow us to easily convert between the representations. And if you go back to some of the examples that we covered earlier in the lesson, you'll find that it is in fact possible to convert between the representations, sometimes quite easily and directly. And that is the end of the lesson, which has been all about channels. We talked about what they are, and we took a look at some basic examples. We discussed three ways that channels can be represented, and we dove into some technical details that establish the equivalence of these representations. I hope you'll join me for the next lesson, which is all about measurements in the general formulation of quantum information. Goodbye until then.